Hello, everyone. Thanks for joining in this Facebook Live event where we're going to talk about exploding stars, dark energy, and the end of the universe. Quick answer, it's not going to happen soon, don't worry. We will begin in a minute or two. Now, the way it will work is that I'll talk in the Facebook Live video, in the chat box. You can type your questions. I'll try and answer them as we go, and we'll have some time for some questions at the end. So we'll start in just about 1 or 2 minutes. Hopefully we'll all stay tuned, and you'll learn a bit about what's going on up there, and how cool it is, which, that's always a good thing to have. So, yes, and hello everyone, and yeah, thanks for tuning in. And again, remember to type in the chat box as we go, and we'll try and do some questions. And hello to you, Amalia, as well. And it should be fun. I don't know if anyone tried to get up this morning to see the SpaceX NASA launch. I was up. If you didn't hear, I assumed you heard by now. It didn't quite happen. There was some bad weather, and bad weather happens. It was pretty bad. There was lots of storms. I actually had a tornado warning for a while, and then there's a lot of lightning around. So it meant that it wasn't safe to take off, because one of the tricks is not just the weather at Florida, where the rocket's taking off. You need it essentially clear all across the ocean, because as the rocket goes up, in case something goes wrong, the astronauts need to eject, and they need to splash down in the ocean, and they don't want to land in a tropical storm or rough seas or anything like that. So they obviously wanted to play it safe. The next scheduled time will be 3:22 p.m. Saturday U.S. Eastern Time, which is 5:22 a.m. Sunday morning Australian Eastern Time. And if that doesn't work, then it'll be Sunday U.S. 3 p.m. Eastern, Monday 5 a.m. Australian Eastern Time. So let's hope that it works. Let's hope it's successful, and that it's a new start to something cool in space. And so today we will be talking about things that blow up, stars, things that make up our universe. Something that's called dark energy, and ultimately how this is going to affect or change the universe. Now, the great thing about this talk is none of this is going to happen on a fairly quick time scale, so you do not have to worry, but doesn't mean we can't enjoy it anyways. And again, reminder to, in the Facebook Live chat box, type your questions. I'll answer them, trying to answer some as we go, and then at the end, we'll have time for some more. So let's get started. And we have to get started with our universe. And this is kind of what our universe looks like. This isn't to scale or anything like that. This is trying to put in perspective what our universe is. Our universe is about 13.8 billion years. The current measurement is 13.83 billion years, give or minus a couple 100 million years. It's big. And it's big because the universe is growing for a long time. And it's actually more than just essentially how far we can see in light years, or how old we say it is in light years. We currently measure the universe, if you were to say side to side, ultimately, it would be 93 billion light years across. And when we talk today, and when most people in astronomy and cosmology, like what we're talking about today, we talk about the observable universe. What is the boundary we can measure and we can see, and the limit to what we can understand? And that is because the universe may be bigger than that, but there's a limit based on the growth of the universe, its expansion, as we'll talk about the accelerated expansion, that puts a limit on what we can do and see and measure. And so it could be even bigger than that. And that's kind of the exciting thing. And this is really a bit of our timeline. And, we are down here on this far right end, and this is where we'll talk a bit about what's going on today, relatively, today being billions of years. When we go backwards, though, the cosmic microwave background, that happened about 380,000 years after the Big Bang. And that's pretty much the furthest type of light, this is microwave light, that we can see. And it's a real type of light, but it's trying to understand how the beginning of our universe was. It came from what we call the Big Bang, a singularity, a single point, and went under rapid expansion, what we call inflation, which is kind of a mystery. The universe went really fast, we were really big, and it's kind of been cruising along and getting bigger. And so we're really talking about what's going on in this period, what's going on nowadays. How is the universe growing so much and so big and so fast? And in order to do that, we first have to talk about what's in the universe. And there's kind of three pieces of a cosmic pie. I wish I had some pie right now, but that's a different story. We have dark energy. We'll focus on that today, and that makes up about 70% of everything. We also have dark matter, and dark matter, we're not going to really touch on today, but it's a real thing. It's a type of matter, mass stuff, that makes up a lot of the mass in galaxies. Now, dark matter and dark energy are not related. It's not like E equals mc squared. It's just one is matter, and we can't really see it, and one is energy, and we can't really see it. We're just not really creative in the naming, but that's a different story. And ultimately, dark matter is kind of like gravity. It interacts with gravity and pulls things in. Whereas dark energy, it's like gravity in reverse. It's pushing the universe out. It's pushing and growing the universe. And then the smallest piece of the pie is really the remaining about 5%, and that is stuff, atoms, things, us. And, hopefully, maybe some of you have seen this or flashing back to high school, and the periodic table of elements. Now, I really like this table because this final line is complete. They found some more of these elements. They've been measured and created in the lab. But this isn't even the full amount of atoms, the full amount of stuff in the universe. In fact, this is the real periodic table of elements. And luckily, you don't have to memorize this one in school. It would be a bit of a trick there. And what you're seeing here is every line is essentially a previous square. So if we look at helium, for instance, helium being down here, helium can really come in a few different ways, and that is because of the amount of neutrons. So if we look at an atom, we have protons, we have neutrons, and we have electrons. You can change the amount of neutrons in an atom. And this slightly changes the element, slightly changes the property. And so elements in some ways can kind of mutate. And some of them are quite abundant in the universe. If we look at helium, helium-4, as we call it, the normal helium, 2 protons and 2 neutrons, the stuff that you find in party balloon gas and those sorts of things. It's actually quite rare on the Earth. We're running out of helium-4. But helium-3 is kind of an exciting type of fuel because it could be used in fusion sources, and we think the moon is rich in helium-3, or at least has more than the Earth. And it may be something that can be used to create and help future space exploration. That's one of the goals. In fact, when we saw with the SpaceX launch, it's more than just going to the space station, it's going onto the moon. So there's lots of these different things out there, and they make up the stuff in the universe. They make up our Milky Way. This isn't an image, and that's because we can't actually take an image of the Milky Way. We're sitting looking into the galaxy. So when you go on a dark night, you see the band of stars and gas going across our sky. And that's because we're kind of sitting on the edge, like we're looking through the Frisbee or the dinner plate of the Milky Way. But the Milky Way is 100,000 light years across, meaning if you stood on one side and turned on a light or a torch, it would literally take 100,000 years for it to get to the other side. And we know our sun is kind of roughly here. We're a bit, we're in between the center and the edge of the Milky Way. And in real units, it's 95 quadrillion. So more than a billion, more than a trillion, it's a quadrillion. So it's 95 followed by 15 0 kilometers wide. It's big. And yet, our Milky Way isn't the only galaxy. There's multiple galaxies, something you can see with your own eyes. If you go on a really dark night here in the Australian skies or the southern skies, and you look towards the south, you'll see the brilliant Milky Way. And this is taken from Chile. And you can see these two faint fuzzy clouds. And this is what we call the Large Magellanic Cloud, and that's the Small Magellanic Cloud because one is large and the other is small, and they look like clouds, and Magellan named them. Again, we're not really good at this naming thing, but these are what we call dwarf galaxies. These are real galaxies that are slowly being collided or pulled into our Milky Way. And so you can see other galaxies with your own eyes. And we can even go further and take a look at something like this, which is called the Hubble Extreme Deep Field. So this is an image from the Hubble Space Telescope that essentially stared at a blank patch of sky. And it just took an image, the equivalent of 23 days. It essentially stared at the same part of the sky for 23 days. And this is what it saw, where every single dot, except a few, like this one, every single dot, from the big things like here that clearly look like galaxies to these faint smudges in the background, is an entire galaxy like our Milky Way. And our Milky Way has 300 billion stars. And we think all of those stars have planets around it. There could be billions to trillions of planets in our galaxy. And yet our galaxy is probably only one of 2 trillion galaxies. Because in fact, this image is taken from this little piece of sky. So if you go out on a nice full night where the full moon is, this is how big the moon is in comparison to that little patch we're looking at. And that little patch is this, 20, 30, almost 50,000 galaxies in here. And so if we think about all the big sky, we think there's 2 trillion galaxies, and those galaxies have stars, and those stars have planets around it, and those planets have moons, and yet that's 5%. All of that is 5%. There is a lot of stuff in the universe, and a lot of stuff that we're just trying to understand beyond what is the stuff that we know. And this is where it comes to be with dark energy. Now, to talk about dark energy and the growth of the universe, we first need to think about the universe in general. What do we mean by the expanding universe? So the way to think about the universe is, imagine you have a balloon and you draw dots in the balloon, or maybe you made a cake and you put some Smarties or M&Ms on the cake, or chocolate chips. What happens is you blow up the balloon. What happens is you pump air into the balloon, or what happens to the cake as you bake it? It grows, it rises, it spreads out. And with the balloon, you're not creating new stuff, you're stretching the balloon. With the cake, you already have the ingredients there. It's just expanding, it's rising. And so every dot on the cake or the balloon is moving equally away from everything else. So as the universe expands, as it gets older in time, as it goes from the Big Bang to today, the galaxies separated apart, but they move apart from everywhere else. So right now, if you can see the entire universe and you can see all the galaxies and stars in it, everything would be moving away equally from you. So everything is moving equally away from you right now, but it's also moving equally away from me and my dog on the couch and everything. And so the universe is expanding equally in all directions. We cannot see an edge, we cannot see a boundary, and it's not like we're creating new universe. We're just stretching the universe that's already there. And so if we stop the universe growing and go backwards, everything shrinks. Just as if we deflate the balloon or the cake starts to implode. It gets smaller and shrinks, and so everything gets closer together until we go backwards to the point in time and we get to the Big Bang. And so it's important to think about the universe this way. It's expanding in all directions, and there's not a center, there's not a sphere, and it's trying to understand what that really means. So if someone's ever said you're the center of the universe, well, you kind of could say you are, but so am I. We all are. There isn't one center. And the way we start to measure and understand these things are techniques or tools in space. And the one we're going to talk about today is what we call standard candles. So imagine you're standing on a street and you have a street bulb right next to you. Imagine you can take a light meter, or you can measure the energy output of that light bulb, so you know exactly how much energy or how bright that light bulb is. Well, light fades with distance. And it's a cool rule. It's called the 1 over r squared law, that light fades to the 1 over the distance squared. So the light bulb 1 meter away is much brighter than the light bulb 2 meters away. And that's much brighter than the light bulb 4 meters away, and 8 meters, and 16 meters, and so on. So imagine you're on the street and you measure how bright that light bulb is, and you look all the way down the edge of the street to the furthest light bulb you can see, and you can measure how bright that light bulb is. So if you know how bright your bulb should be, say here, and how bright the light bulb appears to be at the edge you can see, you can figure out how far away it is. And in space, our light bulbs are supernova. These are exploding stars. And so this is the galaxy over 50 million light years away. And so we see lots of dust and gas swirling around. We see the center here where there's probably a big black hole. And we see this little star here. And that little star is what we call a supernova, one exploding star. So an exploding star can actually outshine the light from the entire galaxy. So to put this into scale, one supernova equals 100 million, billion lightning bolts. So imagine one lightning bolt, one of the things that stopped the SpaceX launch this morning. Then imagine 100 million, billion of them. That is what happens when one single star explodes in the universe. They are powerful, powerful explosions. Now, the cool thing is they happen a lot. So have a think about it. How often do you think stars explode? Once a year? Once a decade? Once a second? So in a galaxy like the Milky Way, there's about one that explodes every 100 years. Now, the last one that exploded in our Milky Way was in 1604, so we're overdue. And if we think about how big the universe is, those 2 trillion galaxies and all those stars, every second, there's 50 stars that explode. 50 stars explode every second. So on your 1 hour lunch break, 180,000 stars have exploded. 180,000 solar systems have boom. And when the star explodes, the planets go with it and the moons. So it's a really big place. And the cool thing is they're bright and there's a lot of them, which means there's a lot of these tools to use. Now, someone just asked, is the expansion caused by a continuation of the Big Bang? Now, we're going to talk about that in a second because that's a very good question. And it's related to what we're measuring in the growth of the universe and what we actually think may happen to the universe. That's a good question, and hold on to it because we're going to talk about it in a minute. And someone also just asked, why are most galaxies shaped like spirals or rings? And this is a good question. And in fact, if you saw last Friday, there was an announcement from the European Southern Observatory, which saw a swirling ball of gas and a planet being formed. And that's because in the universe, things spin around. And as you spin things around, imagine you're spinning a ball and things start to collide together. Well, as soon as a few things collide together, it gets more mass and gravity. And so that starts to pull other things to it. So then other things are starting to pull closer together. And then more things collide and gravity pulls it to more together. So it spins more and more, and then more and more, and then more and more until you get pretty much a disk. So solar systems, rings around Saturn, the galaxy, all form because of the way spinning and essentially angular momentum work in the universe. That's a really good question. Now, our light bulbs, there's a lot of them, and they're bright, which means they're easy to find. Now, the cool thing about finding supernova, it's pretty much just spot the difference. That's literally all we do. Now, in the old days being 20 years ago, people did this by eye. Some people still do this by eye, but nowadays we have computers to help us do it. And ultimately what we do is we take an image, what we call a template image, an old image, then we take a new one. We subtract the two, the things that don't change go away, and then all of a sudden, boom, there's a bright thing at the center here. So in fact, you can see this galaxy is a bit bulgier over here. It's a bit bigger in the center, a star has exploded. Whereas the rest of these galaxies haven't changed. So I want you to play spot the difference at home. And I'll give you a minute to do this, and I'll explain how to do this. So we have an image here on the left. And then 4 days later, we took a new image on the right. So this is our old image. This is our new image. So there should be something new in the right image and not the left image. So you want to look for something brighter and in something that's not really seen in the left-hand image. Now, I'll give you some clues. If we look here, so these galaxies here, they're very bright, but in this case, they're faint. Now, they're fainter because the moon's a bit brighter. So you want to see something brighter in this right-hand image compared to the left-hand image. And if you see things like this little square here, or there, or there, these are what we call cosmic rays. They're kind of like cockroaches in the universe. They're passing through us all the time. Don't worry about it. And so sometimes they hit our cameras. So you want to see something bright and new on the right-hand image that is not on the left-hand image? I'll just give you a second to see, and I'll tell you the answer. We'll see how good you can be a supernova hunter. And I really loved this game as a kid, finding Where's Wally and Spot the Difference, and I still play that, but don't tell anyone. And this is what you get to do. So if you've seen, did you see here? There's this little bright dot there that's not there. And some of you may have noticed the center galaxy is a bit bulgier here. But there's actually two things. That is the supernova, and that is a supermassive black hole that just swallowed a bunch of gas and stars and burped. So that happens too, but that's okay. Now, we have other ways of figuring out what's an exploding star and what's a black hole swallowing things. And this is how we find these exploding stars, is this spot the difference. And it's really cool. And so if we survey lots of parts of the universe and lots of images, we can find thousands and thousands and thousands of exploding stars. And stars explode in two ways. And let's talk about this for a second. So now lots of stars are big. Our sun is relatively small. So imagine a star 8 times or more massive than our sun. And there's lots of these. And in the inside, we have kind of this battle between gravity pulling the star in and pressure pushing the star out. So a star, our sun even, gets its heat from what we call nuclear fusion. So we take atoms, we smash it together. That creates something slightly heavier, but we also get energy out. So it's like a nuclear bomb. And so every star is smashing these things together, creating more heat and pushing or creating more energy, but also creating heavier things. So it creates some heat, pushes it out, but it also creates some heavier things in the inside. So then gravity starts to pull the inside a little bit more. So to counteract this, the star burns a bit more fuel, which creates a bit more weight, so it burns more fuel, and so on. So there's this battle between burning enough fuel and pushing the inside of the star outward so it can survive, and gravity collapsing it in so it crushes itself. And at some point, the star can't keep it up. And the bigger the star, the faster this happens. So kind of like a car, the bigger the car, the more fuel it goes through. And at some point, the star kind of gives up, and gravity collapses the inside of the star together. So we call these core collapse. The core collapses. We're very descriptive people. And as the core collapses, so imagine you take a scoop of dirt or sand and you squeeze it and squeeze it and squeeze it until you can't squeeze it anymore. The moment you squeeze it anymore is the moment you create a neutron star or black hole. So in fact, in this process, neutron stars or black holes are created. And then your hand bounces off. The star bounces off in the center, and it produces a shockwave, and this ignites the star. And the star ignites, explodes. So in the death of these big stars, we create black holes or neutron stars, and the star explodes all in the matter of minutes. And in fact, we've now been able to capture the moments of a star exploding using a cool telescope called Kepler. Now, some of you may have heard the Kepler Space Telescope, and it's actually famous for finding planets around other stars. But one of the cool things that it does is it takes an image of parts of the sky every 30 minutes. And so if we want to see the first minutes of a star exploding, we are actually able to use Kepler to capture it. Now, what we'll show is a kind of an animation of what we saw. So we have a big star here, and this scales in minutes, so literally in minutes. So we're taking an image of this star. Now what's happening on the inside of the star, it's collapsing in. We're squeezing it, we're squeezing it, we're squeezing it. We've created that black hole, we produced a shock wave, it rips apart the star ignites, and then it blows up. So this literally is happening in the span of an hour to 2 hours. And using this powerful telescope meant to find planets around other stars, we're able to see stars explode, to see the shockwave rip apart, to see the moment a black hole is created or a neutron star, in the moment a star is ignited. Now, the cool thing that happens when stars explode is the star explodes. Now, obviously, the planet explodes with it, which is unfortunate, but you're literally blowing up all of the atoms that make it up, all of the protons and neutrons, everything separates out. And this is something kind of cool. So this is every dot is 30 minutes. And we get to a peak brightness here. So the explosion is happening, and then the star cools. And then we got this other bump. And what this other bump is the moment that the stars cool down and the atoms start to come back together to form new things. So literally the atoms, protons and neutrons, start to come together and form new hydrogen. Because in fact, if we look at the periodic table of elements, they're actually created in different types of ends of stars' lives for the most part. So you might have heard the famous saying from Carl Sagan, you're made of star stuff. Well, you're actually made of dead star stuff. That's okay. And so we can trace back where the elements on the periodic table of elements come from. So things like hydrogen mostly come from the Big Bang. Helium comes from mostly the Big Bang, but a bit of exploding white dwarf and big star. Now, some elements we think only come from exploding big stars. Some come from a mixture of big stars and small stars, and some come from completely different things. So in fact, you are literally part Big Bang, you're part exploding big star, you're part exploding small star. You're kind of a mixture of these things as well. And it's kind of amazing to think about the stuff that makes us up is really from this process in the universe, that as these stars explode, even though it's the end of a solar system, the end of the planets, it eventually comes together to form new stuff. The universe recycles itself. And by seeing this process, it helps us date stars. In fact, we know our solar system is the third generation. So our solar system and our sun came from a previous star that died, and it came from a previous star that died. We're the grandchild of the family. And so we can find a way that the universe does this process and grows and changes and evolves by seeing these things happen. So it doesn't tell us just about things ending, but it tells us about things beginning as well. Now, one of the cool things we've also been able to do is actually see the star explode directly. So this was a supernova called 1987A. Now, supernova get their name, SN is supernova. And we have a kind of a list. So the first supernova year is A. So this was the first supernova in 1987. Then the second is B, and we go all the way through Z. Then we go AA through ZZ, and then AAA through ZZZ, and so on. So it's kind of this nice process that happens. So this supernova occurred in a large magellanic cloud. So if you imagine a couple of slides ago, we talked about those neighboring galaxies we can see with our own eyes. This supernova exploded in it. It was very bright. And this is what we saw on the left, this huge explosion. Now, someone realized that telescopes like the Anglo-Australian telescope at Siding Spring, north of Canberra, had actually imaged the stars in this galaxy. And so they looked what happened before. And they said, hey, there's a star exactly at the same position as this explosion. And this star happened to be what we call a blue supergiant, a big puffed out star. And after a long time, the light faded, it cooled, it went away, and this star is gone. So we're actually now able to see the star before it explodes, see the star explodes, and then confirms it disappears. So really confirming this life cycle in essentially real time. Now there's another way stars can explode, and this is the important one for what we're going to talk about in a second. And that is, imagine you have what's called a white dwarf, and I'll show it in a second. And a white dwarf is something our sun will be in 10 billion years. And a white dwarf is a really heavy star, about anywhere between half to 2 or 4 times the mass of our sun. So it's a really heavy thing, but it's tiny. Most of the star has puffed out, and it's kind of been condensed down into this big ball that has still most of the mass and therefore most of the gravity, but isn't very big, isn't very bright. And if this star, this white dwarf, gets too close to things, it can actually act as a vacuum cleaner. It can actually suck off the atmosphere. Now, as I said, a white dwarf is something our sun will be in just 10 billion years. If you look at what our sun is now, it's about 4.6 billion years. It has another 5 billion years, so it becomes a red giant. So this will puff out, it will grow, and it'll shed its layers into a planetary nebula and then be left as this white dwarf. And that's pretty much all that's going to happen to our sun. But lots of stars are in 2 or 3 star systems. So imagine you have a white dwarf and it goes through this phase. Well, what happens if it's close or has another star in its solar system? It could actually act as a vacuum cleaner. And it pools, it sucks off the gas or the atmosphere of this other star. And it reaches a critical point, 1.38 times the mass of our sun, and it explodes. And it produces a shock wave, that travels through space, like in the big stars, and slams into the other star. So if we can detect the shock waves, we know the shock wave happens when it reaches 1.38 times the mass of our sun. The shock wave travels through space, it slams into the other star, it actually pushes the other star, and we can kind of see this ignition, we can kind of see this interaction. And if we can see this interaction, we can confirm the level of explosion because there's a cool equation we can use. E equals mc squared. Energy equals mass times the speed of light. When you blow up at a certain type of mass, 1.38 times the mass of our sun, then you release a certain amount of energy. We have a light bulb. We know exactly how bright it should be. And if we confirm how big the shock wave is, we can measure exactly the nature of the explosion and get a better estimate on that energy. Now, the other way stars can also explode in this case is if you just have two white dwarfs that can actually collide into each other. Now, in this case, they spin closer and closer, they crash into each other, and they detonate. When they detonate, they produce a quick flash, but it doesn't slam anything because there's nothing to slam into. So by seeing the absence of the shock wave, we can kind of also measure the star that explodes and figure out that mass to understand our energy, to understand our brightness, to get our distance. And this is exactly what we did with the Kepler Space Telescope. So again, this is in days here, so that's, our explosion happens to about 20 minutes, 30 minutes we pinpointed. And we can actually see, is it a big star that was involved in this white dwarf, something 6 times the mass of our sun, 2 times the mass of our sun, or is it 2 white dwarfs colliding? And because we saw nothing, we determined it was 2 white dwarfs colliding. So we know the type of explosion, and we know the mass, and we can measure the brightness. We've seen another one where we actually see this little excess, and we know that it occurred with a star 6 times the mass of our sun. And therefore, we can know the mass, we can know the energy, we know the brightness. This is our light bulb. So by seeing these shock waves travel through space, we can get a good measurement of our light bulb. And what we can then do is measure distances. So because the explosion should be about the same way, so it takes anywhere between 15 and 20-ish days for it to explode, we know that they should all be the same brightness. And so we can measure it or squish it to get the same brightness. And if it's the same brightness, we have our light bulb. And what we've done is this. We're actually able to see the growth of the universe. So this is speed or velocity down here, and this is distance. And if you have, so we're down here, all the way over here. This is the Big Bang way down here. So imagine the universe is expanding, 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 speeding up. If the universe was just growing, it would be a straight line. But it's getting faster and faster and faster and faster and faster and faster and faster. In fact, this little orange box down here is what Edwin Hubble and Henriette Leavitt used to measure the growth, the expansion of the universe. And it's been expanding. And someone asked about the expansion, is it a continuation of the Big Bang? And so we have to think about this accelerated expansion. So the Big Bang happened, and the universe was growing. Now, the universe, the expansion, as you said, would be a continuation of the Big Bang. But what people thought, people like Brian Schmidt, who led the project that initially discovered the universe was accelerating 20 years ago, was that the universe would actually stop growing. Why? Because you have mass, and mass has gravity, so it slows down that expansion. And eventually it would stop. And then gravity would start to pull everything back together in the reverse, something we call the Big Crunch. But why is now the universe speeding up? So not only is it expanding, it's getting faster in its expansion. It's growing more today than it did yesterday. So the universe is growing literally more today than it did yesterday. Tomorrow it will grow more than today, and so on. So this can't be explained by just the Big Bang expanding, the Big Bang expansion. If it was just growing at the same speed, it would. So that's a very good question, because that shows that there actually has to be something else out there causing this expansion. And in fact, as the universe gets bigger, it's growing more universe. And we call this dark energy, because it's kind of like gravity acting in reverse. As the universe gets bigger, it's growing more and more, and it's not pulling things together, it's pushing things, which is a bit strange. How is it pushing things? Nothing that we know of really pushes things. So if there's something that's pushing the universe to grow, there must be something else in the universe, and this is what we call dark energy. And it makes up about 70%. To see this growth, to see this expansion, it has to make up about 70% of everything in the universe. Now, and it can't be explained by dark matter, it can't be explained by anything else. Now, the interesting thing about this is as the dark energy causes the universe to grow, it will actually cause the universe to end. Now, as I mentioned before, we thought maybe this big crunch would happen, that the universe would stop expanding, gravity would pull it back together and it would crunch in on itself, a reverse Big Bang. We don't really think that's going to happen. The universe is speeding up. So what we're trying to do right now is measure exactly how fast the universe is accelerating. And two options can happen. One, the big rip, or the other, what's called the big freeze, or constant dark energy, or the heat death. Now, I think the big rip is kind of cooler, and the other one's pretty depressing, but I don't get a choice in it. But we don't know either. Now, the big rip says that the universe grows so fast that the actual fabric of the universe can't keep it up. That space-time itself, it's growing too fast. It's running out of energy. And at some point, the universe rips apart. It's kind of hard to imagine this, that the fabric of the universe, space and time itself, ripping apart. And it would actually be the end, essentially instantaneously, of the universe. Now, the other option is what we call heat death or big freeze. And that is the universe just keeps growing and growing and growing. And it gets so big that galaxies are so far apart, we don't form new galaxies. And then eventually, the process of stars dying, and that separates out. So we don't form new stars, and then so there's no new planets. And then eventually, atoms and nuclei, the stuff that makes us up on the atomic level, so far apart, we're not creating more of it. So the universe just kind of ends up in this empty, cold place. And that's it. Now, I said it's kind of depressing. I don't like it. That's okay. So we don't know which of these options is going to happen. So what we're trying to do is measure the speed, the acceleration of the universe. That will tell us what dark energy is, and that, or a clue to what dark energy is. And then that will tell us what are these options of the end of the universe. Now, again, all of this is so far in the future, we don't have to worry. But because we see this weird growth, we see this fast growth, the universe is doing something funny. And that's what we're trying to understand. But there's actually even a slightly crazier problem. And that is this. If we go back to this figure, we can measure the speed at the furthest point we can see. And we measure it in terms of kilometers per second per million parsecs. So it's kind of like a chunk of the universe, which is about 3.1 million light years. So the universe at the beginning stage, as we can see, was growing about 68 kilometers per second per 3 million light years. So fast. Nowadays, today or locally nearby, we measure it to be almost 74 kilometers per second per 3 million light years. This is the problem. Why aren't the speeds the same? We've understood the acceleration, the speeds aren't matching up. What have we missed? What have we messed up? Now, one of the things we noticed was the measurement here is not as good as the measurement far away. So we wanted to find a new way or a better way of measuring it. And we actually turned to something called parallax, literally trigonometry. If you ever have learned trigonometry and wonder who uses it, I do. I use it all the time. Trigonometry is actually very useful. So students, if you're in school, you will and can use trigonometry. It's a useful tool. And you could do this to measure the growth of the universe. So imagine, so hold your finger out and close one eye. So close your left eye. And then open your left eye and close your right eye and blink them a couple times. What do you notice? Your finger moves differently compared to the background. What if I know how far away my eyes are? If I know the distance between my eyes, I can use trigonometry to figure out how far away my finger is. And in space, we know a very accurate distance, and that is the distance between the Earth and the Sun. We know it to be about 498.6 million kilometers, about 93 million miles. We know how it varies. So we can take an image in July, and then 6 months later, we can take an image in January, like we're blinking our eyes. And we can use trigonometry to figure out how far away that star is. But we found an even cooler way. And that is, we took the Hubble Space Telescope, and we took this image. You might think this looks terrible, and we did this on purpose. We take this smeared image. And that is because what we noticed is we know another distance really well. we know the distance and height of the Hubble Space Telescope orbiting the Earth. So we can take an image when it's on one side and an image when it's on the other side. And then we could do that in January and July. So it's like blinking and then taking another step and blinking. If we know how far away that step is and we know how far away our eyes are, we can get a more accurate measurement to our fingertip. But there's even something subtler than that. If we zoom in here, the Hubble Space Telescope shakes. It has a bit of shake. So instead of acting like one blink, it's like all these little shakes happen the same across every star. So it's like we're just constantly walking around and blinking, which means we can get measurements literally millions of times more accurate to the distance around us, and therefore get a measurement of the speed a lot better and a lot more accurate. You know what we found? Essentially the same thing. And this is interesting because now our two speeds are pretty accurate and they don't agree. What's going on? Well, if we look at our pi, it could be that we don't really understand some of the actions of atoms, but that's unlikely. It could be we don't understand something about dark energy and that's throwing off all these measurements. But dark matter is understood a lot different way. It could be we don't understand the effect of dark energy and maybe it's doing something funny and messing up the speeds in our universe. Or maybe we've just missed something and there's something else. And so this is what we're trying to understand, is what is else out there? What is this dark energy? And what's going to happen to our universe? And these are all intertwined together. And this is kind of the very interesting thing, is that we can use this to understand what will happen to the universe, how it will end, and actually what makes up the universe in a very cool way. Now, we'll do some time for some questions. So someone asked, are most galaxies that shape because it swirls around because of the gravity at the center, which is pulling elements and everything in it? So if galaxies are spinning around, is it because the thing in the center? Not quite. And that's actually because the center doesn't actually have that much mass. It has some, but the entire galaxy is balanced out. It's a conservation of the spin and actually angular momentum. So it ends up being something kind of uniform and going together. So how long can you see light from a supernova for? So how long do supernova last? That is a very good question. So supernova lasts depending on how big they are. So they can last the majority anywhere for 40 days. You can see some supernova upwards of 300 days. It kind of depends how far away it is and how big your telescope is to detect the light. So even if say Betelgeuse, say a star in our Milky Way blew up, it would be very bright and we'd be able to see it for probably with big telescopes upwards of at least a year, if not more. So if anyone has any more questions, feel free to ask. We'll take one or two more, and we can always answer more in the chat afterwards. So I think someone again asked earlier, is the expansion caused by a continuation of the Big Bang? And so again, that was a good question because partly yes, but there's partly something else that's taking over that we're trying to understand. So, you know, I hope you have had fun and understood a little bit about our universe, about exploding stars and what makes it up and how the universe may end. Tomorrow, there will be a public night on the Mount Stromlo Facebook page, and I'll be doing the stargazing if it's clear. And if not, we'll be trying to do other things. There will also be a special talk that we'll be doing in a couple weeks, chatting with me, open to friends of Stromlo, and you can look at the Mount Stromlo Facebook page to understand more. We'll talk about some of the current events in space. You do have to sign up for that, so take a look. So I hope everyone had fun, and if you have questions afterwards, you know, feel free to post them in the chat. And if not, luckily our sun won't explode, so you don't have to worry. But the end of the universe will happen at some point, but it's not going to be next week, so we still have to go to work and pay our bills. So take care.